Okay, so let's look at this chapter. This is chi-square test. Okay, so chi-square test, let's see why we have to learn chi-square test. It's used to test whether a particular type of distribution is appropriate for the data given. So that means, let's say our data is normal distribution or not, or our data is binomial distribution or not, or our data is Poisson distribution or not. So in order to determine that, we can use chi-square test. Test statistics involve square. Okay, and because of that, we only interested in upper limits critical values. So what happened is because of the square, right? So we only have the right tail. Okay, we don't have the left tail now. So the chi-square test can only be used to test two lists of frequencies, the observed frequency and the expected frequency. So we have two lists of frequency. Yeah? Okay. Calculated from the hypothesis. Okay. So we have this formula to count the chi-square value. So the chi-square value is sum of observed frequency minus expected frequency power 2 over expected frequency. Okay, so of course, one thing to highlight for the expected frequencies. So we need to know expected frequency, right? Normally, we count expected frequency by using NP. Okay, by using NP, yeah. So our expected frequency equal to probability of x equal to I times total frequency. Total frequency. Okay, now let's continue. Okay, yeah, next point. When calculating, set up a table as follow. So your variables, probability, observed frequency, expected frequency, and then you count the chi-square. Then you total up them. Okay, so now, next point. If the expected frequency for a class is less than 5, then you must group this class with the next class. So normally the expected frequency, which is less than 5, happens at the first or the last row. So it happens at the first row, and then you combine with the second row. So that is greater than 5. Okay, so if expected frequency that is less than 5 happens to the last row, then you combine with the second last row, so that it is greater than 5 at the end. So we want that to happen. Okay, so if you add up 2 rows and it's still less than 5, then you add up with one more row. You combine 3 rows to make the EI greater than 5. So once that happens, then only you count the last column. You have to combine the EI first before you count this. Okay, so now hypothesis when testing. Now hypothesis, okay, so it's generalized in this way. The something distribution, or maybe normal distribution, or maybe Poisson distribution, is a suitable model. The distribution is not a suitable model. Okay, so this is the general way to write down the hypothesis, and let's move on. Okay, so comparing the chi-square, comparing the chi-square values. So first, once you have calculated the chi-square value of the data given, you must then compare it with the critical value of the chi-square distribution. Okay. So that means the calculated value is based on the formula just now, the OI minus EI squared then over EI, then you sum up everything, that formula. So you count that, and then you compare with the chi-square critical values. Of course, this value you have to check the table. So when you check the tables, of course you need to use two information. One is the degree of freedom, another one is the significant level given. So okay, for example, let's say you see the second point here. To test 5 classes at a 5% significant level, find the critical value of the chi-square distribution at 95% with 4 degree of freedom. Okay, so that means the degree of freedom is 5 minus 1. 5 minus 1, so you get 4. Okay, then the 5% is always the right tail. Okay, it's always the right tail. It's something like this. Your graph is like this. So the 5% is here. Then the 95% is here. Okay, so it's the right tail. So you check when you check the table, so you take 0.95. You refer to 0.95, and the degree of freedom is 4. Okay, degree of freedom, of course, you have to remember one thing. You know, degree of freedom, the formula is V equal to n minus 1. So the n, right, must be the number of rows after combine. You know, when the EI is less than 5, you have to combine, right? So after combine, then how many rows remain? That will be the n. So n minus 1. Okay, then after that, if the distribution fits, the calculated value should be less than the critical value. That means you accept HO. So the HO region is here. The big region is HO region. So critical value is here. The calculated value is, if it's less than the critical value, then you do not reject HO. Do not reject HO means you say that they fit. So the data fit. The distribution fits the data. Okay, so it's just to check whether they fit or not. So goodness of fit to prescribed distribution types. Okay, so this is the case where the null hypothesis states that the data has a particular distribution, but does not specify all the parameters of the distribution. So let's say, for example, they said they fit the binomial distribution, for example, but they never mention the parameters of binomial, like the n and the p. They never mention. Okay, so you must then calculate the parameter in order to carry out the test. Okay, so example, that means they don't give you the parameter. They don't give you the what kind of parameter. Let's say, for example, you can see the note here. For mean, right, we're supposed to have 2 parameters, the mean and the variance. Okay, Poisson, we have to, the parameter is the mean. Binomial, the parameter is the probability of success, the p. Okay, so you must then calculate the parameter in order to carry out the test, and that means you have to count it. You have to count all this, because it's not given. So for k parameters calculated from the observed data, you must subtract k from the degree of freedom, V. Hence, with m different outcomes, V equal to m minus 1 minus k. So that means, normally our degree of freedom is just minus 1. Minus 1. Okay. Why minus 1? Of course, this is because of the total. So we have to minus 1. Or we just minus 1 without knowing the reason sometimes. Okay. But now we have to minus with k as well. For example, for normal distribution, if you need to count mu and sigma square, then k is equal to 2. You do minus 2. For Poisson, if you need to count the mean, then you have to minus 1. For binomial, if you need to count the p, the probability of success, then k is equal to 1. So you have to minus with the k before you check the table. So okay, let's see here. One quick example. Discrete uniform distribution. So what is discrete uniform distribution? Of course, it is something like this. You have probability as the y-axis, and then x as the x-axis. So they have the same probability. The integer values of x has the same probability. Okay, so example, a die is rolled 300 times and the frequency of each score recorded. You know, for a die, right? So it's just 1, 2, 3, 4, 5, 6, and then they have the same probability of 1/6. You know, for a fair die, it's going to be like that. Huh? So that is a discrete uniform distribution for the fair die. Okay, now you have a die that rolled 300 times. So you want to see whether your data fit with the discrete uniform distribution or not. Okay, so 1 to 6, the frequency are as follow. Test whether the die is fair at the 2.5% level of significance. Okay, so we set up HO. HO fit the discrete uniform distribution. H1 doesn't fit the discrete uniform distribution. Okay, now after that we have to figure out the expected frequencies. Expected frequency EI. We are doing this for 300 times, so we use NP, right? So N is 300. Probability to get each score is 1/6. So then 50 should be the expected frequency. Huh? Okay, so then we have the score 1, 2, 3, 4, 5, 6. Then we have the observed frequency, just copy back only. 43, 49, 54, 57, 46, 51. Expected frequency 50 for all of them. Okay, then we have the OI minus EI square over EI. Okay, so let's say I just take from what I count before, 0.98, 0.02, 0.32, 0.98, 0.32, 0.02. Okay, then I total up the last column, I get 2.64. Okay, so this is what we call the test statistics. So the chi-square is 2.64, test statistics. Okay, now we need to count the degree of freedom first before we look at the table. So degree of freedom, V equal to n minus 1. So 6 minus 1, which is 5. Okay, now we have to look for the table. So our significant level is 2.5%. Okay, 2.5%. So 2.5%, imagine something like this, 2.5% on the right tail. Okay, so 0.025, 0.975 on the right tail. Okay, then degree of freedom is 5. Okay, so we look for MF19 again. So there's a table which is known as chi-square distributions. Okay, so this is the one. Degree of freedom is 5. This one. Then the probability on the left hand side is 0.975, so we have 12.83. So this is the value, 12.83. Okay, then after that, let's come back. Okay, so 12.83. Okay, so our calculated value is just 2.64, which is inside the big region, which is the HO region. So we just make a conclusion: do not reject HO. So the die is fair, and the die is fair. Or you can say it fits the discrete uniform distributions. Okay, that means this HO, right? If you don't want to say fits discrete uniform distribution, then you just say the die is fair. And this one you say the die is not fair. So two options for the HO and the H1. Okay, so we stop here first. We continue the rest next time. Okay, so now we have the next subtopics, which is continuous uniform distribution. So for continuous uniform distribution, first we need to know that it looks like this. Then we have the y-axis, which represent the fx, and then fx is the function that tells us the graph. The graph is a horizontal line. The x-axis is x. So we have something like this. Okay, so compared to discrete uniform, if you still remember, it is like many vertical lines, as you can see here, many vertical lines, and this one is one horizontal line. Okay, so the uniform is because of the horizontal part here, so that's why it's uniform. So this is very similar to the discrete uniform distribution. Pay attention to the class boundaries and find the expected frequencies. Okay, so what are they talking about is, let's say I give one example. So they say pay attention to the class boundary. So what kind of attention should we take? Okay, so let's see example. So I put a very simple example just to let you get the concept on it. So my variable, I put two value on it, 0 to 1, 2 to 3, just two intervals. The observed frequency, I put 14, 16. Okay, so in this situation, we need to set up the class boundary. So which is, you see there is a gap there, a gap of 1 unit from 1 to the next one, 2. So we should set boundary as 1.5. Okay, so 1.5, which means you have to add 0.5, and here you have to minus 0.5. So the boundary is hence negative 0.5 to 1.5. The next boundary 1.5 to 3.5. So the expected frequency is based on the continuous uniform distribution concept. We have a total frequency of 30, and we know that this is NP. The basic concept is NP. So N is 30, and then the P is 1 over 2. So the P is 1 over 2 because we have only 2 class interval. So 2 class interval, then they take the probability of half. Okay, so 30 times half, so 15. We should expect the frequency to be half for each 15. Okay, so that is how we get the expected frequency. And after that, you have to count OI minus EI square divided by EI. So this part I skipped. So our attention is the class boundary and the expected frequency. So this part and this part is a little bit special. Okay, now we look at the next distribution, binomial distribution. Okay, so the information given here, they said for null hypothesis, the binomial distribution is a good fit. So this is one type, but sometimes our null hypothesis is having more details. The binomial distribution B 30 0.3 is a good fit. So this, for the first one, they don't give us the N and the P. For the second one, the N and P is written down. Okay, so it will affect the degree of freedom actually. So you can see here, we use the mean of the observed frequencies to calculate the expected frequencies. And so both OI and EI give the same mean and total. Thus, there are 2 linear equations connecting the frequencies. Okay, and V equal to N minus 2. So they are trying to explain why we have to take this degree of freedom, N minus 2. Okay, because of 2 linear equations basically. So that's why you have to minus 2. Okay, minus 2. Okay, so for the second case here, if 30 and 0.3 is given, then they explain it in this way. The means using OI and EI will be different means. Thus, there is only one linear equation, the total, connecting the frequencies. And so, V equal to N minus 1. Okay, so they are trying to explain why this is N minus 1 and why this is N minus 2. You know, if you know what are they talking about, then it's good enough. If you don't know what are they talking about, just take it or just memorize it. They seldom ask for explanation. Okay, so we just memorize it, like if the N and P is not given, N minus 2. If the N and P is given, then N minus 1. Okay, so we can take it in that way. Okay, so of course the reason behind is because of 2 equation and 1 equation, So now let's look at the next one, Poisson distribution. Okay, so maybe we should look at one example for binomial distribution first, before we look at this Poisson distribution. For binomial distribution, okay, let me see the question first. The question for binomial distribution. Okay, so it is a question on page 19. Question on page 19. Okay. Okay, so a scientist carried out an experiment to investigate the quantity x, which takes the value 0, 1, 2, 3, 4, 5, or 6. He believed that the values taken by x follow a binomial distribution. He conducts 250 trials. His results are summarized in the following table. Okay, so you can see the table over there. So they give observed frequency. Okay, so now part 1, show that unbiased estimates of the mean and variance for these results are 1.876 and 1.266 respectively, correct to 3 decimal places. By evaluating the mean and variance of the distribution binomial 6 and 0.313, explain why x could have this distribution. Okay, so let's show this first, okay, before we consider the next part. So we find the mean. So the mean, we use this formula, sum of fx over sum of f. Okay, so to find out sum of fx, so basically we need to multiply the 0 with the 22, 1 with 83, and add up the products. So multiply first, then add up the products. Okay, so you will get 469. Divide by the total frequency, so we total up the observed frequencies, we get 250, and then we get 1.876. Okay, so we managed to show it, and now we have to show the variance also. So for variance, sigma square. Okay, so we can use this formula, 1 over n minus 1 sum of fx square minus sum of fx power 2 over n. Okay, then after that we substitute 1 over 249 sum of fx square. That means you take the frequency, multiply with the x power 2, 83 multiply with 1 power 2, and so on, add up the total, and you end up with 1195. Sum of x square is 469 square 250, so you get 1.266. So that is the first part. Okay, now the second part, they said by evaluating the mean and variance of the distribution for this binomial with n 6 and p 0.313. So we evaluate their mean and variance. So let's evaluate first. Okay, so for binomial distribution 6 0.313, so the mean is np, 6 times 0.313, so we get 1.878. Okay, and we find the variance. Variance is npq, so 6 times 0.313 times 0.687. Okay, then we get 1.290. Okay, so by evaluating the mean and variance, now explain why x could have this distribution. So our x here, our data here, the mean is kind of close to the mean here, so the variance is kind of close to this also. So because of that, our data could have this binomial distribution. So we just write in words, x could have these distributions because the mean and the variance are close to each other. Okay, so that is how we answer the question for the first part. Okay, now let's see the next part. The expected frequencies corresponding to the binomial to the binomial distribution are shown in the following table. So they want to save our time. So instead of counting NP one by one, the P itself is kind of troublesome already, for each binomial with this x value, you need to count the probability and then multiply with n. That is troublesome. So they count for us. Show how the expected frequency for x equal to 4. For x equal to 4, the expected frequency is 17.0. So you just need to show one time only how you get 17.0. They just want to make sure you know how they get this value. Okay, so first we need to find out the probability for x equal to 4 by using the binomial probability formula. 64, 0.313 to the power of 4, and then 1 minus 0.313 to the power of 2. And then we press calculator, we get 0.06795. So once you get the probability, then the expected frequency is n times the probability. So the n is 250, the p is 0.06795, and then you will get 17.0. So we handle it in this way. Okay, now on the next page, part 3, test at the 5% significant level whether the scientist's belief is correct. Okay, so the scientist's belief. Okay, so if you look at the front part of the question, what they said in front is they said he believed that the values of x follow a binomial distribution. He just believed this thing. He never said the binomial distribution has to be binomial distribution of what kind of n value and what kind of p value. Then he never mentioned that. Okay, so he never specified. He never say something like he believed that the values of x follow a binomial distribution 0.313. He never say the n and the p. So if this is the case, right, the degree of freedom is n minus 2. So this one is a bit tricky. This part a bit tricky. The n minus 2. So if you misunderstand, then you end up with n minus 1. Okay, so we set out the HO. The binomial distribution fits the data. H1, the binomial distribution does not fit the data. Okay, so then we work out a table. We'll build a table like this. So we just need to copy back the data from the previous table, and we get 22, 83, 72, 53, 1730, and we copy back the expected frequency given 26.3, 71.9, 51.8, 49.7, 17.0, 3.1, 0.2. Okay, so remember one thing: if your expected frequency have value smaller than 5, we need to combine. So for example 0.2 and 3.1, these two are smaller than 5, we combine. After combine is just 3.3 is still smaller than 5, so we combine with this again and get 20.3. So we combine and get 20.3. So if you combine 3 values for expected frequency, then you have to combine 3 values for the observed frequency and get 20. And for the last column, you just need to count one value only. So take the combined value and count. Okay, so now the calculation part, I leave it to you. So you just look at the value. You will get this value. So you get this value, and 3 of these you combine and count together, you get this. Then you add them up, you get 3.81. Okay. So once you get 3.81, we need to know this is the test statistics, and now you have to find the critical value. So critical value, remember one thing, we use v equal to n minus 2. V equal to n minus 2. So how many data do we have? You have to count the one after combine. So we have 1, 2, 3, 4, 5. We have 5 data only after combine. So 5 minus 2, which is 3. Okay, so we have significant level, which is 5%. Okay, so we look at the data booklet. Okay, so let's take a quick look. Data booklet, F19. Okay, so we look for the chi-square distribution table at the end. Okay, so degree of freedom is 3, and then the significant level is 5%. So that means you should expect here 5%. The gray color region, this region should be 0.95. So 3 and then 0.95, so should end up with 7.815. So we take this value, 7.815. Okay, so let's come back to our case here. So we write down the critical value, chi-square 3, 0.95. This is 7.815. So of course I just quickly use the graph to explain it. So our critical value is 7.815. So if they are greater than the critical value, they are in this small region, we reject HO. If they are in this big region, then we do not reject HO. So 3.81 is here, which is in the big region, which is the HO region. So we do not reject HO. Okay, so we just write down 3.81 is smaller than 7.815. So do not reject HO, and end up with the binomial distributions fits the data. Okay, so that is how we answer the questions.